management class. I hope you guys are staying well. I know it's tough times out there, so I really hope you're staying healthy and safe at home. What I want to try with you guys today is my first lesson with you guys here. I'm going to actually wrap up Chapter 2 with this 212 repeated sample lesson. Okay, the assignment that I actually uploaded a couple of days ago, that will wrap up the end of Chapter 2. So I know that there's no repeated sample stuff on there, but not to worry, that takes up the bulk of Chapter 2 anyways. But just so that you guys get a sense of what repeated sampling is, I still wanted to work through the lesson, and you can try a couple of the questions at the very end. Okay, so I will pre-warn you, when I write on this iPad, I'm using an app called Notability. Some of you might know it, and I am using my stylus. However, it is really tricky sometimes to write on here, so please just bear with me. I will upload a blank copy of this lesson, the finished copy of this lesson, and also the video link so you guys can follow through. Okay, so today's lesson is on repeated sample, and what I want you to think about is a time where you might have had repeated sampling experiments in the past. Okay, so you might think even back in elementary school when they first introduced the idea of what probability is, you might have gone through a couple experiments, especially with a die. Okay, so a die is a six-sided figure, and it has numbers 1, 2, 3, 4, 5, 6. It is not a dice because the dice is a pair of die, so we're just actually considering one die. Okay, so for our example, if a fair six-sided die is thrown an infinite number of times, we know that the mean of the numbers will be approaching 3.5. Okay, so what does that mean and where does that come from? So what I want you to visualize and think about is if you had a one-sided die, and you actually can do this on your own as your own little experiment if you want to give it a shot, and if you have a piece of paper and a pen, I want you to record your samples for rolling your die 4 times. Okay, so as a sample 1, what happens in this experiment, on first throw, let's say you get a 6. You throw it once again, you get a 2, you throw it once again, you get a 5, and for the 4th time, you get a 6. So if you were to find the mean of those throwing of the dice, or die, sorry, for the 4 times, so adding 6 plus 2 plus 5 plus 6, you would then divide by 4, because you have thrown that die into the air, calculated those values, and then you're now dividing it by 4. Okay, so what ends up happening is you do get a mean of 4.75. You can try this again. So again, sample 2. Let's say you throw it into the air. On the first try, you get a 2, a 3, a 1, and a 6. You add up those numbers, divide by 4, or 4 throws. You now get a mean of 3. Okay, so for this experiment, it was actually done 3 more times. So we have 5 samples. Okay, and we actually have all the means already calculated for you, as you can see in the last column. So if you wanted to figure out what the average of your means were, or the mean of the means, what you would do is you would take all of your mean values, so in the last column, you would add them up. So 4.75 plus 3 plus 3 plus 2.75 plus 3.5, and you should get 17. Okay, now like we did with the single means, to find the mean of the means, we would take 17, and we would divide by the amount of experiments. Just going to make that a little better. Okay, so we did 17 over 5, because we had 5 experiments. Now 17 divided by 5 is 3.4. So this means that the average of the 5 times that you actually threw that die into the air and calculated the means out of it, the average of those means was 3.4. So our sample size was consistently 4, right, because we did 4 throws. And notice that only one of the samples has the correct average, and the first sample is far from the actual mean. Okay, so it approaches 3.5 as we saw in that earlier statement. So we can see when we actually get a mean of means of 3.4, we are still actually approaching 3.5. And your key ideas, so if we take the mean of the means, we get a result of 3.4. So although the mean of any one sample may not be a good predictor of the population mean, we get better results if we actually take all of the means and find the average of them. Now, this leads us to this idea of the central limit theory. Okay, so the central limit theory considers what happens when you have repeated samples of an experiment. Now remember, it always has to be the same size, right? So your sample size needs to be consistently the same. And when it's drawn from a population, we have to consider two things. So the sample means will be normally distributed with a mean equal to the population mean. And the distribution of the sample means will have a standard deviation of, okay, so we have our mu symbol. Okay, so the sample means will be normally distributed with a mean equal to the population mean. Okay, so this means that your sample is pretty much going to represent your population mean. Okay, and then secondly, the distribution, the sample means will have a standard deviation of this equation. So standard deviation will be equal to standard deviation divided by your sample. Okay, so to find the standard deviation of your means, you'll take the standard deviation and divide it by n. And it's the square root of n. Okay, so that will be a handy formula that we will use later on. As a keynote, a large sample size is required to have more than 30 because that gives us a reasonable estimate of what the mean is, and also for information on our standard deviation, right? So anything less than 30 isn't as accurate. However, when we have more than 30, it obviously does provide us a better picture to look at. Okay, so we'll go through our first example. So for our first example, we have an example of a car. So I'll just read through the example with you. The tires on a rental car fleet have lifetimes that are normally distributed with a mean of 64,000 kilometers, a standard deviation of 4,800 kilometers. Every week, a mechanic checks the tires on 10 randomly selected cars. How likely is the mechanic to find a sample mean of 62,000 kilometers? Okay, so this is actually what we're trying to figure out. This question is broken down into several sub-questions, so we can go through that as well. Okay, so what is the population mean? Okay, so remember our population mean is given to us where we have 64,000 kilometers. Okay, so our sample mean is going to represent our population mean. Okay, so the sample that we're choosing. And in that, we are given a mean of 64,000 kilometers. Now for our next question, what is the standard deviation of the sample means? Okay, so they do say that the standard deviation is 4,800 kilometers. So I'll just write this in our given. Okay, so our standard deviation is 4,800 kilometers. Okay, now what is n? Now it says every week a mechanic checks the tires on 10 randomly selected cars. So that means there are 10 cars, okay, and he's going to check all the tires. So there's obviously 4 tires on the car. So in total, that mechanic is checking 40 tires. Okay, so to find the standard deviation of the sample means, we're going to use that formula we discovered in the previous page. So the standard deviation of the sample mean, so you see that subscript of x bar, is equal to the standard deviation divided by the square root of n. So we're going to replace that with 4,800 divided by the square root of 40. Okay, and what you should get after working that out in your calculator is 759. Okay. Now, we were asked in the bottom of our example 1 question is how likely is the mechanic to find a sample mean of 62,000 kilometers? So we want to see what is the probability that we can actually find a sample mean of that given kilometer base. Okay, so yes, this means that we have to interpret and use our z-scores. Okay, so z-score is equal to x minus x bar divided by your standard deviation. Okay, so we want to find a sample mean of 62,000, so that becomes our data point x. Okay, x bar was 64,000 divided by our standard deviation. Okay, so once you work that out, you do get negative 2.64. Okay, so with that information, we need your z-score table. Okay, so I did post one in case you don't have yours handy at home. So you're finding the probability that the average is going to be less than or equal to 62,000. Okay, so when you look up negative 2.64, you should get approximately 0.0041 once you use your handy z-score table. Alright? Okay, so hope that makes sense. We'll carry on then to our second example. Okay, so for our second example, the population of males aged 35 to 44 in Canada has a mean systolic blood pressure of 130 mmHg with a standard deviation of 8 mmHg. For the probability that a random sample of 50 males has a mean systolic blood pressure. Okay, so we're going to consider a couple of different cases. So we're going to consider what happens when it is below 133 mmHg, when it's above 128 mmHg, and when it's within 2 mmHg of the population mean. Okay, so once again, we'll go through what's given to us. Sorry. Let's try this again. Give it. Okay, so for our population mean, we have 130. So again, our sample mean is equal to our population mean, which is 130. To find our standard deviation of the means, we have to take our standard deviation, which was 8, and divide it by our sample, which was 50 males, so the square root of 50. Okay, this gives us approximately 1.13. Okay, now if we were to take this into a normal distribution diagram, okay, so we have our normal distribution curve. If x bar is approximately at 130, okay, we want to see what happens from 133 less than that value. Okay, so below 133. Okay, so once again, we will take our z-score table, and we are going to calculate z is equal to 133 minus 130 and divided by 1.13. Okay, this gives you a z-score table to look up at 2.65. And then, if we want to find what is the probability that x is less than or equal to 133, we look up 2.65 and we get 0.9960. Okay, you're actually going to repeat these same steps for above 128 mmHg, and then within 2 mmHg of the population mean. Okay, so for instance, if we have 130, within 2 would be like 130 adding 2, which is 132. Within 2 to the left would be 130 minus 2, which is 128. So you're going to find what's under this curve. Okay, just for the sake of time of the video, I will post these solutions, but you guys can try this on your own first and then just have a look with your solution key. Okay, and lastly, for your example 3, okay, so this reads, the score on a standardized reading test are known to be normally distributed with a mean of 10 and a standard deviation of 1.5. So we want to find the probability that a single individual selected at random scores between 9.4 and 10.6 on his test. Okay, so this is similar to what we've done with the 2 points. Okay, this is just written in a word problem setting. So essentially, I'll draw the curve there for you. We are given a mean of 10. Okay, we want to find scores between 9.4 and 10.6. Okay, so we'll do that same thing where we use our data point of 9.4, consider the values that we are given for this, which is a mean of 10 and a standard deviation of 1.5. So we have this z-score, or we'll do the first z-score of 9.4 minus 10 over 1.5. Okay, so as you can see, this question is phrased differently from how the earlier questions were phrased. Okay, so we just go back and scroll to example 2. Right? So the population of males aged 35 to 44 in Canada has a mean systolic blood pressure of 130 mmHg and a standard deviation of 8 mmHg. Okay, so that's already looking at a group of values. How this question differs is it says the score on a standard reading test are known to be normally distributed with a mean 10 and standard deviation of 1.5. Find the probability that a single individual selected at random scores between 9.4 and 10.6. So basically this follows the same format of what we did in our z-score section, right? Where you just take the value itself, a point value. It's not a repeated sample type question. Whereas the ones in example 2 and example 1 did represent repeated samples. Okay, now if you look at the second part, you guys can finish that up and you can take a look at my answer key. If you look at how this is now phrased, find the probability that a random sample of 25 students has a mean score between 9.4 and 10.6 on this test. So the key word here is that a random sample of 25 students. It tells you that there's been a random sample, whereas in the above question, it just references the single individual. Okay, so for a question that's phrased in this way, yes, you would have to apply the standard deviation of the mean of means.
No. Oh, you're smiling.
Okay, where we're going to take 1.5
Baby.
and divide it
Baby
by
smiling.
the sample.
Hi, good morning.
Okay, so we get then 0.
Good morning, Kingston. Hi. You smiley facey.
Now, because of that random sampling word, again, that's just some extra piece that you need to make sure that you have in there by doing careful reading. Whereas you see in the above example, it's just a single individual versus a random sample. Okay, even going back to example 2, right? A random sample. So look for that keyword of random sample. And that random sample means that you actually do have to carry through with that formula. Okay, so I will finish up these solutions and then I will post them for you. Okay, I do want you to try it first just to kind of see if you're gathering what the lesson is trying to, I guess, get across. There are a couple of questions on the back page that you can do here for your own learning, and they have the answer key right at the very bottom. Okay, so hopefully that was clear in terms of the last section in this unit. So again, this is repeated sampling, and please don't hesitate to message me if you have any further questions. Okay, thanks, take care.